there was this. We have
I'm very happy to introduce today Thomas Rincevicius. Okay. I can consider him as a friend. We have been working together for about 4 years within the framework of an European project. And he is the one that is going to open this program awarded by Cátedra Sanca of Nanotechnology. It's really an original program that aims to invite external professionals in order to give you a vision of how nanotechnology and how nanoscience can be moved to reality and can be a way of surviving in this world. Okay, so the topic today is related to SERS, surface-enhanced Raman spectroscopy, and I think this is, as Thomas will explain just in a while, is a success history. Okay, so Thomas, I just mentioned that he is the co-founder of the company, and now is the CEO. Among the current activities are business development, SERP applications, and of course, sales. Okay, the relevant experience and knowledge of Thomas is about nanoplasmonics, plasmomechanics, molecular detection, spectroscopy and microscopy techniques, microfluidics, and for sure, SERP applications. So, Thomas, I think is the time. The time is for you. The floor is yours.
Thank you, Maria. Can you hear me well?
Yes, I think so.
Yes. Okay. Okay. So first of all, thank you, Maria, Andreas, Marta, for inviting me. I mean, it's my pleasure to be a part of this Thursday's NanoSpin-off talk, and because it's a university, I made the talk a little bit towards science. We can, of course, speak about company and the business if you like in more detail. I have some slides at the end about the company. But so the title today of my talk is nanopillar-based structures for SERS applications. And I will try to convince you that the SERS is a good technique and that the substrates that we chose to work with work well for some of the applications. Okay, so as Maria mentioned, I am working part-time at SILMECO APS, and most of the time actually at DTU Help in Denmark, so Technical University of Denmark, as a senior researcher. Okay, so the scope today, I'll try to talk a little bit about nanoplasmonic structures, because this is the why we have SERS, and then Raman surface-enhanced Raman scattering, spectroscopy, nanopillar-based structures, and then a little bit about optical properties, what makes these structures interesting, useful, and then I will give some examples of applications, and then talk about the company, and then most of my talk will be about these nanopillar structures that you see here. So if we start about nanoplasmonics, I know that most of you probably at least heard this name, and they know that nanoplasmonics is not a new area. It has been around for many years, actually probably more than 100 years already. And typically when people speak about nano-sized gold or silver particles, you probably heard this term plasmons or localized surface plasmons. It means that the nanoparticle, when you shine light on a nanoparticle of this size, say 100 nanometers, there's something strange happens. So the nanoparticle is able to support these LSPRs. And if you look at the sort of exact theory, let's say Mie theory that solves Maxwell's equations for sphere, I mean, it's very complicated, at least to me, to understand physics behind. Right, so I often like to turn to this quasi-static approximation, like what you see here, basically that encompasses the essence of plasmonics, at least localized surface plasmons. in my opinion, it's easier to understand physics behind. So it's a quasi-static approximation. Well, the word quasi, because you use frequency dependent on the electric function here of metal when you describe the optical properties of nanosphere. But here, basically, you consider that nanoparticle is much smaller than the wavelength of light, and the field that you shine on nanoparticle is basically constant across. And then, as a result of that, you can derive rather simple sort of explanation of, why nanoparticles absorb and scatter with certain properties, like why peak is in certain position, why its particles appear in a certain color. Right, so here I basically have in the bottom two equations, scattering and extinction cross-section, and extinction here means absorption plus scattering, because when we speak about nanoparticles, both terms matter. And here you have the alpha polarizability for sphere. It's very easy to understand where the resonance comes, why you see a peak. When you put a colloid in a spectrophotometer and measure spectrum, you typically get a peak of colloidal particles. So the resonance appears here because of this bottom part here, that when it goes to zero, you start to see the resonance. Right, and then of course the question is why these nanoparticles behave like this, and then you can couple light to these conduction electrons. They start to oscillate, and we create these quite localized surface plasmon resonances that are frequency dependent and the shape of nanoparticle dependent. And then you can basically think of it as a way to confine the light to small volumes, but this basically focus tremendously. And here you see two plots, like a single sphere and two interacting spheres, like the incoming field is tremendously enhanced, right? So you have sort of a small hotspots here on the single sphere, and you can have true hotspots when you bring two spheres together. For the polarization parallel to the particle axis, you can get a strong interparticle coupling. And so this is again quite simple to understand it, because in these terms you can think of two interacting dipoles. Okay, you bring dipoles together, something happens depending on the polarization. And then when two particles brought together, this is example of two disks, but similar effect is for the particles too. So when they brought together, notice here on a right-hand side that when they're very, very close, the resonance is actually shifted tremendously compared to when they are basically very far apart, or if they are single. So, and this is important because when we have particles that are closely spaced and we get to these hot spots, we need to also remember that if we want to use this for source, well, we need to actually be able to predict or know where this peak is located, so we can adjust our laser closer to the resonance peak. That's why when you look, for example, here in this picture to the left, it's actually impossible to say whether these are single particles or interacting. Maybe there are actually two particles close to each other, not necessarily different shape, but it could be two particles close to each other, giving a different color because they're interacting. Right, so this is a dark field image. And then I will just briefly overview Raman spectroscopy. I think most of you know Raman spectroscopy. You for sure heard about it. You know that it's a very popular technique that helps you to basically, in research at least, helps you to study basic properties of the matter. So it can be liquid, solid, or gas even. In industry, it's mostly used to identify materials. As you can see here, a handheld device can identify an unknown material, right? And because each material has its own specific Raman spectrum fingerprint. And then application areas vary, they're widely spread from pharmaceuticals to forensics, illicit drugs. This, for example, where we work in. So just to remind you that Raman is not new, it's already widely used. And what we want to add on top of Raman is SIRS, to enhance capabilities of Raman spectroscopy. And why do this? Why we need SIRS? Well, because you see Raman, like what you see here on the left-hand side, is inherently actually quite weak process. So you, like this is an example of the picric acid molecule, but you're not able to detect low quantities of material using Raman, right? So it is useful if you have like a pile of unknown powder on your table, then you can identify it, or fluid, maybe like ethanol or methanol. But as soon as you start decreasing concentration, well, Raman is a weak effect, so you basically stop identifying, you stop seeing your analyte. So for that reason, people thought, well, since we have these nanoparticles that seem to have a hotspots here, extremely high electromagnetic fields that we talked previously, what would happen if we put molecule directly in between these particles? Well, and it turned out that this Raman signal can be significantly amplified. And this is an example with the two spheres, but of course you can have variety of different nanoparticle structures. And then it becomes possible to detect fewer molecules. So then now it can actually work as a sensor. Now we can maybe use in diagnostics, maybe it can be used in analyzing, environmental samples where you have a small quantity of molecules. And we will come to that. And now, one more slide I added here to those who are familiar with SIRS, and you've probably seen this term that intensity of SIRS is proportional to the power of force of the local field. You've probably seen this formula. And here I just wanted to outline that there are typically two ways that people think about it. So more intuitively here on the left-hand side, you can think of when the incoming field is interactive particle, so the particle enhances the incoming field, right? So the molecule is feeling the already enhanced field by the particle. So there's one channel, and then the molecule also, molecule scattered around light is enhanced again by the particle. So you basically get two E squared multipliers. So you intuitively can feel where the power of 4 comes. But in my opinion, even easier way to understand this is this coupled dipole system. When you think about particle and a molecule as two interacting dipoles, then you can think that because this is a sort of simplified dipole moment equation, where, for example, a molecule which has one polarizability feels the incoming field, but also field emitted by the nanoparticle. And also particle not only feels the incoming field, but also a field emitted by the molecule. So it's like a coupled dipole system. And actually, it's not so difficult to solve the system by inserting here the correct fields. You can actually arrive to this term. And see, and there are no multiples here. You have only the dipole sort of terms. And this is quite, at least to me, intuitively easy to understand where this term power to the fourth comes from. And now, why use SIRS? We turn now to a more practical questions, because, well, it's a rather competitive method and very sensitive. So some of you may know that research, was able to even push it to a single molecule detection level. And also that it's not a new research. It's quite old. So it's at least 50 years. Has been recently celebrated 50 years of SIRS research. So there are lots of interesting findings, and probably most of things about SIRS were explained already. What is even more important that the handheld Raman instruments are becoming smaller, better, and cheaper. So it's no longer a problem for a university or a small company to buy a Raman instrument. They are getting really cheaper, and it's being pushed, to the limit where maybe soon it will cost as much as a mobile phone, right? So SIRS then becomes irrelevant in this aspect because Raman instruments are cheap. And of course, there are a broad range of applications over the years have been demonstrated. Sort of on a more complicated side, there are huge variety of SIRS substrates. So basically every university, every group, every company have their own substrate that they prefer and they work. So there is no, at least in my opinion, a unified SIRS substrate picture. So source substrate have their advantages in specific areas, of use. Some are more suitable, say, for gas sensing, like, for example, substrates that, Professor Maria and Pilar is working together with Reyes, they are more suitable for gas. For example, substrates that we are working on, they are more suitable with sort of direct droplet deposition. Some substrates we've seen are more suitable if you incubate. So there is no, at least in my opinion, no universally best substrate or anything in the world, because it's highly dependent on the application. But what makes a good source substrate? I think there is this very nice article from probably one of the inventors of SIRS, Richard Van Dijn here, that basically talks very well about describing, well, what characteristics we need to have in order to say that this is a good source substrate. So I recommend, if anyone is interested, to check this out. So in this article, he basically, well, lists some pretty maybe obvious things, like we need to have a predictable and reproducible SIR enhancement, right? Because the source substrate, think of it, it's an amplifier. An amplifier, we want amplifier to work the same way every time and to produce exactly the same amplification, right? It's natural. Then we want to be able to tune our amplifier, right? So, for example, depending on which beta we want to use. And then we, of course, want that the amplifier is uniform across the area. There's not one point. So typically it's the surface. So I want to have a substrate that you measure essentially, well, ideally, this could also add good substrates typically need to be also cheap, rapid, and scalable fabrication process, because you need many in application development. And also, ideally, you also would need batch-to-batch reproducibility, meaning that when you come to fabricate substrate on different days or different months, when you make a different batches, they should be as similar as possible, right? And then we turn to this method, what we call maskless reactive ion etching, is because it was basically cheap and easy. So at the time we were working also with some of the applications, and we wanted something that we can have, many substrates we could fabricate fast. And then one researcher at Anabonsis group, Michael Schmidt, he started to sort of work on just etching silicon without any masks, and just looking if we can create some corrugations on the surface. And here you have a few parameters to worry about in this area. So basically chamber pressure, power, etchant gases. So you typically have two. So etchant and the passivation, gas flow, and time. So even though it sounds like many parameters, but actually the windows are not so wide to operate. Right. So here I wanted to just visualize how this looks in practice. I mean, when you insert a silicon wafer, just a clean silicon wafer into a chamber, how the reactive ion etching start with basically physical ion etching, because you need to cut through this oxide layer on a silicon that typically is very thin. Then the next step, you have a chemical etching. Now the SF6 basically starts to etch chemically silicon. But then at the same time, you have also some portion of oxygen that creates a passivation layer. So make sure that you don't over etch. And then you basically repeat these steps, one after the other, and you create this kind of corrugation. And if we simplify at least at this moment, just think about it as a pillars. It is essentially a one-step process. So you do the etching, you create the pillars. On the next step, you deposit metal film, and in principle, you have your substrate. Of course, there is a third step technically to cut the wafer into chips, but that is typically done outside the clean room. So it's not a clean room process. Yeah, so it's a two-step process. And then in simplest, like the first structures that we fabricated look like this. They look more like pillars. And this is the thing, not, I believe this was not evaporation, but sputtering that creates more like a columns, so more uniform coating. But because they are so dense, they're not very uniformly coated. And then if you look from the top, the structures, at least some reasonable scale, looks rather uniform. And currently we work on a 4, 6-inch, and even 8-inch wafer sizes, mostly actually on 6-inch, but 8-inch is also possible. And then now I would like to turn to the second sort of interesting part of these substrates. So first is that it's easy to fabricate. The second is that they have this property of what we call leaning effect, is that when you deposit a droplet on the surface and the droplet dries, so capillary forces pull the pillars together and they create these sort of small micro clusters. And if you remember from my earlier slides, it says this is what you actually would want to bring particles together to create these hotspots. All right, so this is what we are doing essentially to bringing them all together. So they are nearly touching here. Of course, these are not spheres like in my previous slides, but yes, the essence is the same. And now we have basically created these clusters. And then, okay, but what happens if we have an analyte? So this is kind of the same with 2 pillars, but when we have an analyte in the solution, so when it dries, now we have a chance to trap the analytes close to the hotspot. This is what we actually want. And we've done some comparisons like leaning versus non-leaning, and it seems like this is a very important step. So here you directly can see that these substrates, for example, would not be very suitable for, say, gas sensing, because you would need to probably pre-lean them before doing gas sensing. But even if you do that, then it would be difficult to get the molecule into, hotspot. And then if you look at the scanning through microscopy, outside the droplet area, the pillars are standing. Inside the droplet area, you can see these small sort of clusters are being created as a result of this droplet drying, where capillary forces pull now pillars together. And then this is how basically it all started. I mean, we've tested these structures of some basic molecules, and it was simple to fabricate. Then the main work was done by Michael Schmidt from Anja Boysen's group. And the first comparison that we did against some substrate that we found on the market back in the days, like 8 years ago or so, for droplet deposition again, because that is important, how you deposit your analyte. For droplet deposition, it seemed like it is a good substrate, at least compared to our competition that we could find. And now we turn to trying to understand, like, why they are performing so well. Maybe we can even do better. And here on the left-hand side, you see basically our kind of first attempt when pillars look more like pillars. So you have a more uniform coating of gold here, like you see here. But it turned out that this is not optimal for SIRS. So we could not get high enhancement, and probably because you have a uniform metal and you prefer to have actually, gaps and more localized structures instead. So here on the right-hand side, instead, you see more like mushrooms, mushroom-like structures, where you have a head separated from the metal film. And here how they look when they lean together. And then questions that we would typically get, like, well, how do you know that the most signal is coming from nanopillars heads here? Maybe also the film is contributing, because we have these small nano holes here, and because also it's a metal, and we know that you can create a surface plasma polaritons that can interact, talk to each other even at longer distances. So we actually managed to rip off the pillars and just test the SIRS performance of the nanohole structure, and we could not see any enhancement. So yeah, so even though you might potentially create some sort of polaritons here on the surface, but they do not contribute significantly to SIRS signal. So we mostly think that is because of the leaning and because of the hotspot between the pillars. And then there are a couple of ways how we try to model it. The first model was simply ignoring the metal film. So thinking about it like a mushroom, more or less. You have a silicon pillar and a head on top. Now this part here turned out to be very important because in the beginning we ignored it. But when we look closer at the CM images, we saw that, well, it's not really sitting on the top. The pillars are actually sharper. And then you have sort of a coated, and you have this silicon cavity kind of inside. And then this turned out to be an important, feature to have. And then the resonance or the enhancement is highly dependent on how wide, for example, is this pillar. So you can tune it across this theoretical simulation, and this is the measurement from a dark field. And then what was surprising the most, at least to me, that the resonance, this one close to the laser that we typically use, turned out to be not due to the cap, but due to this, you see this enhancement at the sort of neck of the nanopillar. And then this, why we thought that we see relatively uniform enhancement over the areas, because when pillars lean towards each other, the necks never really touch. They never really come close to contact. So we don't have these huge variations in intensity. So this was our first attempt to model it. And the second attempt was with the including metal film. And that was also done. Essentially, we didn't see anything very different. We still have the resonance from the neck, but we also now more clearly saw the resonance that belongs to the sort of sphere itself. But I will not go into the details. And so then one property that I mentioned previously, the uniformity. So what does it mean, uniformity? Well, again, when we have a sort of a surface and we measure at different sort of points on the surface, well, the question is how similar is our measurement? And we notice that if you really, really push carefully fabricate silicon nanopillars, you can get quite uniform, reproducible signal. It is difficult to do, but it is possible. So here, for example, on a basically 25 millimeter area, like a line scan, you can see that the signals are, quite good. And I believe this was 10 or 100 micromolar BPE molecule. And now I will turn to applications and try to, show you what have we tried during the years. So one thing that I thought it's worth mentioning is this, several years back, we were part of this consortium or network Raman for clinics. Researchers and some of the industry try to discuss and test SIRS for unmet medical needs. And one of the things that researchers wanted to do is basically test, well, how reproducible is SIRS in general? So what if we take same substrate and the same protocol of, analyte, so the same molecule, same in detail described protocol, and we distribute to partners and ask them to do this with their home Raman instruments, whatever they use. How similar would results be? Huh? And then it was surprisingly not very similar, but still kind of bearable. So we had a large number of partners from across Europe measuring exactly the same with the whatever Raman system they had, handheld device or Raman research grade Raman system. And it was basically I believe we're the only one from industry selected for that. And there were also colloidal particles tested at the same time. And we got I believe, similar results. We had some advantages, small advantages, but at this point we didn't see a big advantage in uniformity compared to colloidal particles. But it was an interesting study, first of this kind. Then we also worked on sort of real-life problems, where we try to detect melamine, so toxic melamine in milk. There's some of the problems you might heard previously, some years ago. People were adding some illegal substances to milk and making it basically a poison out of milk, and many people got sick because of this, and maybe even a few died. I don't remember exactly, but melamine detection from milk is not an easy problem because you have milk, so you have a multi-component now fluid that has, proteins, fats, a bunch of other molecules that basically will interfere. So direct measurement is very difficult. But then we noticed that these nanopillars, they act a little bit like a paper filter. Imagine if you dip the paper filter in a fluid, so it would suck the fluid, right? The fluid would travel. So this is something similar you see here. When the fluid is immersed with some solvent added, only halfway the chip, you see this dark area appearing here. So this is the wetting of the surface, similar way like what you would see with the paper filter. So it's a way to extract your analyte from the milk. So we would add a solvent to the milk, then put this into what we use back in this centrifugal microfluidics. So this is done on a kind of microfluidic platform, centrifugal microfluidic platform. And then you can basically extract this melamine, and the detection becomes way easier. You can clearly see the melamine peak here. And the pillars act as a sort of a filter that can stop all the solids from entering, right? So you basically, if you measure here close to the immersion area, you see lots of solids, lots of contaminants. But as you go and measure further away from a surface, now you start seeing a more clean and nice melamine signal. Okay, so it's a one way to filter your real life fluids. And then another application that I believe we're still currently working on Boyson's group is the detection of methotrexate or MTX in human serum. So this is for therapeutic drug monitoring applications, and it is for the specific drug is for cancer treatment, leukemia. And you may have heard that the cancer treatment basically needs to be done in a correct way. So the drugs have the specific window of concentration that they work optimally, right? If you are too high in concentration, then you basically make body toxic, so people are being poisoned. If concentration is too low of the drug in the blood, then there is no effect. So it's important to keep it in the right concentration. And this is why it's important, because people are very different. So they have this what's so-called different pharmacokinetic, properties, and basically some would clear the drug very fast, some slower. So concentration, even if you give exactly the same, milligrams to different people, you will see that the plasma concentration varies greatly. All right, so this is a way to adjust the concentration. That's why people, at least in Denmark, are running this therapeutic drug monitoring kind of treatments where they monitor the concentration of a drug in blood. And here in the study, we show that you can do this in basically dipping experiments. So you see this fork and 3 chips mounted where they basically in a perpendicularly dipped in a blood plasma containing MTX. And then you basically can extract concentration. We'll put it on a linear curve here. And I believe concentration requirements for this drug was maybe down to approximately 1 micromolar. So it's not a very challenging concentration level. So it was doable in this simple step. Now we have new sort of versions with centrifugal microfluidics for this. Now, just a few words about chemical warfare agents. It's a project that we were together with Maria, Andreas, just recently called sourcing. And this is some of the pre-study in sourcing that we did before, back in the days, trying to detect chemical warfare agents, VX and Taboon. So very, very toxic and poisonous compound that can be used to, harm people or kill. And here we also saw that if we have sort of an ideal, like if we're really careful in fabricating source substrates and we are very careful with removing backgrounds, we can push the concentration down to very low levels. However, when you turn to the real life situations and you want to now repeat measurements on a large scale, different conditions in your clean room, different days, equipment quality varies, then we see that there's a huge variance introduced, and these concentrations are extremely difficult to reach. So this we can only reach when in the research environment. Now another set of applications, back in the days we tried to look at hydrogen cyanide, or actually potassium cyanide in this case, with detecting it in fluids. These were some of the first steps, because this particular application was for people that have a special bacteria, I believe Pseudomonas aeruginosa it's called, that produces cyanide. And the idea was to be able to detect it in breath. So if human exhale and you can detect extremely low concentration of cyanide, you could basically diagnose someone with having this bacteria. And these are basically first steps when we try to see if it is at all possible. And we here you see even in the reference signal we have actually a small peak always on the substrate, so that's why the concentration limits we could not go that low. I mean, it's basically micromolar. But nevertheless, detection of cyanide, now we know it is possible to do even from gas, but you need to employ a little bit more advanced ways to do it. For example, cooling source substrate. And another example I have here is the detection of tamra-labeled vasopressin that we did with colleagues from the United States also some years back. So vasopressin is basically a marker to detect some of the heart problems. And the problem that detection of vasopressin needs to be done at extremely, the concentration levels are extremely low. So this we're talking about picomole regime. And when we tried to do it directly, it was basically not possible to see. It's just too low. And remember, it's all needs to be done in sort of blood plasma. And then researchers find a way to label, or attach a label to vasopressin called TAMRA that produced specific peaks here. You see one 370 and one 510. And then it was possible to push it to picomolar range. However, we also saw that you need to do extremely large surface mapping. So we needed to produce, I believe, around 10,000 spectra to be able to really detect it reliably. And this is the cell, how it was done. So it's, all in one. It has also a heater here. And I believe it was at the end possible to go to the required picomole concentration level. However, remember this is labeled, right? So this is not direct detection. So there is a step when you need to perform a chemistry step to label vasopressin with TAMRA, so you could detect. Yes, and it also involved, like maybe I didn't mention here, the aptamers. So also specific molecules that were functional, and we functionalized nanopillars with aptamers to specifically catch this TAMRA-labeled vasopressin. And another application that we spent quite some time as well, working also with industry, is detection of polychlorinated biphenyls, or PCBs. Some of you may have heard it's a compound that was used by industry by many years, and then it was discovered that it's carcinogenic, and it now actually is everywhere in the environment, even in old buildings in Scandinavia, for example, in waters and in the seas. You can find in fish even this. However, it's very hard to detect. And here, basically, we collaborated with one German company, chemist, being able to testing a method of modifying PCB. So the direct detection of PCB So this, for example, PCB77, is very difficult, even with source. So we cannot go to low concentrations, I mean, in practice. So the limit is, not even micromole. But chemists were able to come up with a way to modify molecule so that we could take a real-life sample, do relatively simple chemistry, and basically replace the score with SCH3 so that it could attach to the nano gold surface or silver, noble metal surface, basically, to increase affinity. And then we saw that, yes, you can increase the sensitivity, although it was, you see, not linear here, but we could see that sensitivity could be pushed down. And then at the end, the issue was that because polyphenol biphenyls appear in mixtures, and there are a large variety of different ones, different versions of these PCBs with different chlorines in different places on a molecule, it turned out that this chemistry step is not working on all of them. So we, the bottleneck was to have a chemistry step that works on at least majority of these PCBs, but it was working on a limited amount. And another example I have here with a specific science sort of a case where we, one group had been working with this diphenyl nanotube folic acid conjugates for some cancer applications, cancer detection application. But what they wanted to know whether their sort of conjugation procedure or the washing procedure, if they can get rid of the free folic acid. And this is where search turned out to be useful because here in the A, you see this tube laying on our pillars, and we can see basically a spectrum of folic acid. And then the question was, is the spectrum coming from the folic acid on the surface of this nanotube or from free nanotube? From free folic acid that is simply in solution, and they were not able to wash it away in the chemistry step. That was the question. And then they basically made a control where they tried to make the same, but testing the washing step where you are supposed not to have folic acid at all. And then we mostly see thermal signal, we cannot see it. So in this example where search was useful for sort of scientific question. And another example that we work with some of the Swedish partners is using this plasma enhanced fluorescence. So it turns out that these nanopill extractions can also enhance fluorescence quite effectively. And they were and still are interested in taking microplastics in water. They basically, collect different samples from lakes, rivers, and so on in Sweden, and then try to see if they can see the traces of microplastic. And this was one way to do it. It turned out to be quite effective. They also now taking it to the next step and working on a project where they trying to use this method to detect microplastics emitted by 3D printers because they think it's a problem, at least in Sweden. So we hope that it will work equally as well as with detecting it from water someday. Now, a few words about the company. I have mentioned that it's not a new company. It was actually founded in 2013, but not much activity was back then. It was just kind of opened and left registered for several years. It's a spin out from back then it was DTU Nanotech, so Technical University of Denmark, DTU Nanotech, but this department doesn't exist anymore. It was converted to this health technology department. And all the fabrication that we do is done in this DTU Nanolab, what is currently called Clinical Facility or National Center for Nanofabrication and Fertilization in Denmark. Here you see our co-founders, so Michael Schmidt, Per, he left the company, but he was one of the co-founders. Myself and Professor Anja Boysen, because in her group we had all this work on nanopillars, and it still continues. Now, a few words about intellectual property. So it's basically based on one there is one essential patent. We have a few others, but essentially it's one important patent that we are licensing. It belongs to DTU and SILMECO licenses on. So there's exclusivity for specific application areas. As you know, typically patent exclusivity is not granted for everything. Typically, it's only focus on a specific area. You have to define it very well, which areas you want. Because if you want everything, then it becomes extremely expensive. But in our experience, and also the way we talk to other startups, tech startups, licensing is still the best way to go because formulating the patent, covering all the costs, it's just too expensive for a small startup company. It's just too high risk that that it will not work. And then we're currently the company working with illicit drug detection. So, for example, heroin, fentanyl is very popular. Chemical warfare agents and toxic industrial chemicals. Now we try to continue, especially what we learned and then discovered during our sourcing project together with Maria, Andreas, and also big interest from detection or identification of bacteria and viruses. This is actually interesting because in the beginning I was quite skeptical how can research be used to identify bacteria, but it turns out, especially now with the development of AI, the identification of different types of bacteria is very much possible using search. So we have some industry partners that are interested in this. And in general, sort of speaking, of course, we now interested in CBRN, military applications, forensics as well, and also medical diagnostics. As far as I know, we have, at least 70 plus publications based on nanopillars. I think there are more, probably if I collect all partners, it's 100 or more. And then we basically do have several industry collaborations. And, there was two now, there is, let's say one bigger, one very small a joint research project. One Eurostars, and another is local Danish, very small. So that is my brief journey on SIRS and SILMECO and nanopillars. And if you have any questions on any topic, company or nanopillars, I would be happy to answer.
Thank you, Tomas. Thank you.
Thank you. I don't hear, but I.
So I think it's open for discussion. If you have any questions, any curiosity about not only science, also how the company is surviving, or at the beginning, I suppose that you have big ups, big valleys, big valleys.
Yes. So typical questions we get is investment. What kind of investment? And the answer is, so when we made a company, the at least majority of co-founders didn't want an investment. They thought that there's no need to be diluted so early, and we could try to do it just by our own sweat, so to speak. So of course there was some investment when you want to open this company in Denmark like APS. So you need to have your own money to put together. So the 4 people putting together to have this initial capital to do some small activities. But I think the initial capital was around 15,000 euros. That was the investment back in 2013. And then based on that, we started slowly to, open a website, and we were interested back in days just to know what is the status of SIRS, what people are working on. And it was more like a curiosity, driven no one thought it will survive for 10 years. When we did this, we thought it would be just interesting to try and see what kind of contacts we get, academia, and particularly we're interested in academia. We thought maybe we'll get good collaborations. And then in the beginning, it was like that, mostly academia collaborations, but then we noticed that around 2018, 2019, there was increasingly more, we started to be contacted by companies.
Mm-hmm.
And then slowly companies actually overtook academia, strange enough, because before 2018-19 we were mostly doing kind of joint research. So someone from academia would contact us, ask about SIRS, the problem that they had, and then kind of together we would try to solve this problem with very, very tiny budget, maybe from their side, symbolic.
Mm-hmm.
Then
And Thomas, about this super, I mean, the testing that you mentioned, that there were many, if I understood well, many cells, substrates being tested for one specific analysis. In
yes,
order to, so many, when you say many,
I mean thousands. Yes,
okay.
because typical situation with industry is if they like the initial test, so they say maybe they can test 10 substrates first, and then they maybe test 50 in the next step substrates, and then they eventually call you and say that, okay, the enhancement, the sort of amplification seems okay, but for us, what is even more important is how reproducible and reliable this is. So for them, this is absolutely key. We often even hear, can you reduce enhancement but increase reproducibility?
Yeah.
Even that I hear people, saying. And then our main problem for the past, 5-6 years is to make it as reproducible as possible, because the clean room, that we use is we have multiple users, so we don't have our own designated plasma etcher. So these machines are accessed by many people, and machines are getting contaminated, and of course we get sometimes pretty big swings in quality and reproducibility. And we had cases in industry, actually quite a few back 3 years ago, when they tested large amount and they just said no because reproducibility. He said the enhancement is good, everything is fine, but it's not reproducible enough. We cannot sort of utilize it for our needs, and often they don't even tell you what is the need. We often have cases where we don't even know what is being tested.
But in that case, it was search technology for carrying out this measurement compared with other analytical techniques, or it was always search and different search substrates?
Okay, so one I can tell you attempt was back in the days where COVID started. So we were contacted by a company who was searching for a method to do it fast, and then they were testing a few different ones. I just remember, I believe that fluorescent based was one,
Mm-hmm.
then SIRS the other, and I think they had a third one. I don't remember what kind. And then they said, okay, we have sort of basic protocol how we want to test if this is feasible, and then we said okay, uh, discussed how to do it, what kind of substrates, did all the pre-study to decide which substrate. Maybe we need to have a optimize, the assay solvent. And then the problem was that there was two big variants at the end. They said yes, in some cases they could see, but when they took the real samples from people. They managed to somehow get access to real samples. They saw that the variance was too big. And I think at the end they went with fluorescent based because it was just better.
Okay.
Yeah, so it's pretty common. But what I can say is quite popular is, for example, illicit drug detection. So we have some specific drugs, like for example, heroin, that typically produces large fluorescence. And direct detection, even if you have a large amount of heroin and you want to you're able to directly measure amount, you typically see fluorescence, so you cannot. So you need SIRS to suppress fluorescence because SIRS can do it, as you know. So yeah, so we also heard some good things like this one, that it was useful for that. And then there is, as you know, we heard very big interest, especially from French army concerning the gas detection. But you are the expert in this area. You know better how feasible it is. But very big interest. We had a colleague in a conference, and he was talking to officers in France that were very eager, and they want something working on a field, something that can detect chemical warfare agents in gas, something reliable, and even the price was not that important according to this officer, as long as it worked well and it's continuous.
And did you identify your competitor in Asia, or do you have competitors in Asia that you are looking every month or not? I mean, or you already that are.
I think the main well, we have, of course, there are many different substrates on the market. I mean, when we compare the performance, at least with the droplet deposition, which we think is mostly used in industry when they're testing is, I think we are performing better for this specific way of depositing. Of course, there could be other instances that other substrates are better, but I think P-SIRS, so the paper SIRS is one example. They're quite cheap, but that's the main advantage. But in our case, we can also be very cheap. And just because you are cheap, you cannot. I mean, then it's a question about volumes. So most people say, okay, can you sell me substrate for €1? Then our typical answer, okay, how many will you buy? If you want to buy 10, then no. But if you want to buy, 1,000,000, then yes. Or okay, even less than that, 200,000, I don't know. Then yes. So it's all about, and for that reason, we're not pursuing, to really be the cheapest, because then it just makes no sense. I mean, as you know, there are no huge application examples of SIRS that have like killer application that would require millions of substrates. As far as I know, it doesn't exist. Not yet. Not yet. So, but the interest is there, and I see that interest from industry is growing. So I'm positive. I'm surprised even a bit because I thought we would be in academia. We were so used to just interact with academia, so we're very surprised positively that people are getting more and more interest we get more interest from industry. Yes.
You want to add something about not only SIRS, about don't be shy. Okay. Yes, no, yes. Maria, no?
It's okay. Even if you get later questions, you can write me and ask.
Yeah, sure. So thank you, Thomas. I think we can stop here. Thank you
No
for
problem.
your talk.
It's
Okay.
my pleasure. Thank you, Maria, for inviting Andreas and Marta for organizing everybody.
See you. Bye.
Thank you. Have a good evening. See you. Bye-bye.
Cerramos, Marta.